This conference will now be recorded.
Very good evening, students. Today we will be discussing the questions.
This conference will now be recorded.
Very good evening, students. Welcome to the POIQ discussion sessions. So today we have picked up few numerical problems from the question paper JEE Main 2021 July session and shift 1. So the first question says the amount of heat needed to raise the temperature of 4 moles of a rigid diatomic gas from 0 to 50 degree centigrade when no work is done. See, when no work is done, let me tell you, this question is actually from heat, as you can understand from here. Not only heat, kinematics.
This conference will now be recorded.
Very good evening, students. Welcome to the POIQ discussion session. So today we are going to discuss few numerical problems from JEE Mains paper 2021 shift 1, and these questions are from the July session. Okay, so July 20th. So let us read the first question. The first question says the amount of heat required to raise the temperature of 4 moles of rigid diatomic gas. Rigid diatomic gas, okay. So to raise the temperature of 4 mole of a rigid diatomic gas from 0 degree to 50 degree centigrade when no work is done is dash. Okay, so there are options like this. You have to find out the amount of heat required, and here see this thing, you look here, when there is no work done. Okay, if we write down the first law of thermodynamics, dq is equal to du plus p dv. So no work done means this is 0, and see from here, if there is no work done, we can infer that the volume remains constant. Volume constant. Okay, so work done can be 0 only when there is no change in the volume. So we can see from here that dq is equal to du when v is constant. So in case of constant volume process, we can write n for n mole gas n cv dt, okay, is equal to du. This is what we can write. Actually, this is the amount of heat required. Okay, this is the amount of heat required. All right. So ncv dt, which is nothing but the internal energy. Okay, internal energy change in the internal energy. So how do you get ncv dt? How do you write, or how do you get ncv dt? Dt anyway you can find out from here. So that will be 50 degree centigrade only. Okay, this is the dt, we have got that. Then What is N? Here N is given as 4 moles. Okay, 4 moles. N is equal to 4. Number of moles is 4. That is also given. What is CV? How do you find out CV? So CV we can find out. See, from this expression itself we can find out CV. CV is equal to 1 over N. 1 over N for 1 mole. Okay, du by dt from here for 1 mole gas. For N mole gas I can multiply N. So for N mole gas you will get this. Okay, du dt. So we know this information also has been given that rigid diatomic molecule, okay, this gas is composed of rigid diatomic molecule. So from here we can see internal energy can be found out from the degrees of freedom. If you know degrees of freedom for this system, then each degree of freedom will carry half RT energy, half RT energy, each degrees of freedom. We have to find out what is the degrees of freedom here for a rigid diatomic molecule. Okay, diatomic molecule, rigid means what? They don't have vibrational energy. Okay, vibrational degrees of freedom is not there. So if we just consider translational degrees of freedom, only translational degrees of freedom, then we can write, say, 3 into 2 degrees of freedom, F is equal to 3 into 2 minus 1, so we'll get 5. So what will be the internal energy then? And also this is for 1 mole gas. Okay, so we'll get degrees of freedom, see, F into that, so F is here 5. Okay, this is for 1 mole gas. Okay, so we can put that CV is then du dt, so we'll get 5 by 2 R. Okay, or we can write CV dt. Okay, anyway we are going to write this one. So CV we have got 5 by 2 R. All right, now let us put this. So I hope you have understood this. See, n CV dt is equal to du. From here itself I can find out for 1 mole gas CV is equal to du by dt. So du, how do you find out? Du or u, how do you find out? Internal energy. Internal energy, we know that internal energy can be found out from the degrees of freedom. If I know the degrees of freedom of the gas, then or a particular molecule, then we know for 1 mole of such gas we will get F by RT. Okay, F into half RT. So F is here 5, so I get 5 by 2 RT, and CV means du by dt, so 5 by 2 R, right? So I get 5 by 2 R. All right, then I'll find out what is this dq. The heat required will be, sorry, hence heat required equal to n CV dt. N is 4, CV is 5 by 2 R, and dt is 50. Okay, n CV dt. So this will make this 25. So 25 into 4 will be 100. So this will be 500 R. Let us match the options, which one has come closer. Okay, so option D will be the correct answer for this question. Okay, so this will be actually 500 R. Okay, let us go to the next problem. This problem says a deuterium and an alpha particle. See, deuterium is actually this 1H2. Okay, and alpha particle means helium nucleus. Okay, 2He4. All right. So this deuterium and alpha particle having equal kinetic energy. So both of them have the same kinetic energy. Enter perpendicularly into a magnetic field. RD, let RD and R alpha be their respective radii of circular path. The value of RD by R alpha, the ratio of RD to R alpha is equal to dash. You have to find out that. Okay. So we know if a charged particle enters into a region where there is a magnetic field perpendicular to the direction of the velocity of the particle, then see we know BQV. See mv square by r general formula is equal to BQV. Okay, you can remember this also. So I can find out this R to be mv by BQ, right? Where the magnetic field is same for both of them, mass will be different, charge will be different. So let me do one more thing. See, this I can write as P, right? This I can write as P by BQ. Okay. See, I know kinetic energy. Kinetic energy is equal to P square by 2m. Okay. Then I can write P is equal to square root of 2m k, where k is the kinetic energy. Okay. Right. So if I put it here, look, I get this is root over 2m k. K is the kinetic energy divided by BQ. Okay, this is the actually general formula for the radius of a charged particle in the circular path, like radius of the circular path of the charged particle when it enters into a region of magnetic field B having direction perpendicular to the velocity of the charged particle. Okay, so I can just write this RD. For RD I can write square root of 2md k divided by B and QD. Okay, and for R alpha, sorry, R alpha I can write divided by B Q of alpha. Okay, now if I take the ratio of these two, see I have to take ratio RD by R alpha, right? So RD by R alpha is equal to, look, I'll write this RD here 2md k by 2m alpha k and BQ alpha in the numerator here BQD. Okay, look, this kinetic energy for both of them are same. Let me write down few parameters over here. See, m alpha is actually 4 times of md. I'm sorry, this 2 times of md. Okay, 2 times of MD. 2 times of MD, where Q alpha is actually 2 times of QD. QD. So these are the things we know, and B are same, and K kinetic energy for both of them are same. Look this, then I get, see 2 also can get cancelled. This is MD. So I get MD by M alpha, and here Q alpha by QD. Okay, QD. So MD is like M alpha is 2 of MD, so it will be actually half, right? See from here, M alpha will be twice of MD, and here charge will be, charge for alpha particle will be twice of QD, right? Then from here actually we'll be able to get root over 2. Okay, so look this first option. So first option will be the correct answer for this question. Okay, so first option will be the correct answer for this question. Let us go to the next problem. So this problem is from vector. So here the question says A and B vector. See, these are two vectors satisfying the relation A dot B is equal to modulus of A cross B, or magnitude of A cross B. Then what is the value of magnitude of A minus B? See, A dot B, see for the given, like from the given condition, we write A dot B is equal to modulus of A cross B, right? So I can write here A B cosine of theta if the angle between A and B is theta, and here I get A B sine of theta. Okay, so from here I can get, see, tan theta is equal to 1. So this implies theta is equal to 45 degree. Now look this one, magnitude of this one. See, magnitude of this we know as square root of A square plus B square minus twice of A, B, and cosine of the angle theta, where theta is 45 degree. Okay, so this is the one. Look then, this I'm getting as A square plus B square minus, see this cosine 45 means 1 over root 2, 1 over root 2. So if I just write this, then the final answer we can write in this form: square root of A square plus B square minus square root of 2ab. Look, the option, first option, this will be the correct answer for this question. Now let us take this question. This is from the nuclei part. Okay, so here the question says a nucleus of mass m emits gamma ray of photon of frequency nu. Okay, the loss of the internal energy by the nucleus is, where the speed of light, c is the speed of light in the options given here. So how to do that? See here, we'll consider the nucleus in the beginning at rest. Okay, it is at rest. So when it is emitting alpha particles, okay, look what happens when it emits alpha particle. Then it moves in this way with energy h nu, since the nu is the frequency of the, sorry, not alpha particle, gamma. It, when it emits gamma photon, then there will be, see, gamma photon will move in this way, suppose in the forward direction. See, to make momentum conserve, okay, linear momentum conserve, this nuclei, the parent nuclei has to move with velocity v in the opposite direction. Okay, it has to move in the opposite direction, right? So what will be the loss of internal energy? That is what you have to find out. Okay, all right, so let us see how we can solve it. So once we get this idea, look, now we can actually go for conservation of momentum and energy, right, to get the loss of energy. Look, conservation, from conservation of, or applying conservation of linear momentum, we can write, see, initially momentum was 0, so final momentum will be how much? So final momentum will be mv, right? So mv, and this is in the other direction, so ac by, actually e by c. Okay, this is the momentum of the photon. So we get mv minus h nu by c is equal to 0. So which will give you v is equal to the velocity, final velocity, v is equal to h nu by mc. So this is the velocity this parent nuclei get after the gamma decay, or after emitting the gamma photon. See here, loss in the internal energy will be converted into, by conservation of, so you can write, by conservation of energy we can write loss of internal energy of the nucleus is equal to the gain in kinetic energy by the nucleus plus the energy of the photon, gamma photon, that is h nu. Okay, So this is from the conservation of energy, we can write. So then see, gain in the kinetic energy, I know this will be half mv square. So v we have already found out from the law of conservation of energy, sorry, law of conservation of linear momentum. So what is that? I will write it here, half m v square. V is actually h nu by mc whole square, and this is plus h nu, right? Look, then I can find, see, I can take this h nu common from both sides. Okay, so m, let us take common, and h nu common. M is already there in common. Okay, so this will be here h nu. So 1 h nu I have taken out, h nu divided by m square c square plus 1. Okay, so let us see the options how they are given. So in which format they have given. Okay, so m we can multiply. Okay, m we can multiply. Let us see if we multiply. I'm sorry, this m is actually multiplied with only this part. Okay, so that's why we had this issue, calculation issue. Okay, fine. So look, then I can directly write. So this will be mc square. Okay, then what I get, this half will be there with this factor itself. So h nu only will be there outside. Okay, I'm sorry, this is the only with this. So this will be this. So finally, what is the answer? H nu is equal to, sorry, this loss of an internal energy is equal to h nu whole into 1 plus h nu by 2m c square. Okay, so this is actually the loss of internal energy of the nucleus. Okay, by this gamma decay. All right, so we'll go to the next problem. So this problem, let me first give you the options for this problem. Okay, let us read also first. The question says, consider a mixture of a gas molecules, sorry, consider a mixture of gas molecules of types A, B, C having masses Ma greater than, sorry, less than Mb less than Mc. That means the mass of the molecule of type C is greatest, then the mass of Mb, then you have the mass of Ma. Okay, the ratio of their root mean square speeds at normal temperature and pressure. Let me give you the options here. The option says, option A, let me write this in red ink, sorry. So option A says it is 1 by VA greater than 1 by VB greater than 1 over VC. Okay. Option B says VA is equal to VB is equal to VC, that will be equal to 0. Option C says 1 over VA is less than 1 over VB, and that is less than 1 over VC. Option D says VA is equal to VB, not equal to VC. Okay, so these are the options. Consider a mixture of gas molecules of 3 types. Okay, and they have different masses, as you can see here. Okay, look, we know the expression for the root mean square velocity to be V is equal to 3RT by M. Just let me cross check once. Yes, this is correct. Okay, so 3RT by M for 1 mole of this gas. Okay, so look, for a fixed temperature and pressure R and T, R is anyway universal gas constant, 3 is a constant number, so the numerator is actually constant. Then what I can write from here? I can write V is inversely proportional to the molecular mass of the gas molecules. Okay, then what we can write, if MC is greatest, see from here, see from seeing this, what we can write? So I can write VA is greatest. Okay, then it will be VB, which is greater than, sorry, this no, I'm sorry, this is, look, VA is greater than VB, VA is greater than VB, and VB is greater than VC. This is the thing. Now if you take the inverse of them, then this sign will actually change. Okay, then see, if I write 1 over VA, then this sign will change, then 1 over VC. Okay, so look the option, yeah, so this option will be, option C will be the correct answer for this question. Okay, all right, now I'll take few more numerical problems from here, like so there is a problem, numerical problem, which says let me write down the numerical problem here. Question number 6. AC voltage V of T is equal to 20 sine omega t. I think I have this question. Yes, I have this question. Sorry. So AC voltage V of T is equal to 20 sine omega t of frequency 50 Hertz is applied to a parallel plate capacitor. Okay, the separation between the plates is 2 millimeter and area is given. Okay, that means, you know, if I have a parallel plate capacitor, the separation between the plate is D, so that is 2 millimeter, and area of each plate is given as 1 meter square. Okay, that means uniform. Okay, we can take the field inside uniform. The amplitude of the oscillating displacement current for applied AC voltage is. So you have to find out displacement current. Displacement current ID. Okay, what is this displacement current? Which is oscillating between the plates. Okay, or oscillating. So oscillating displacement current you have to find out. See, whenever see that means you know what we are doing. We are just charging. See, let us consider the situation here that see capacitor can be charged by both by DC battery as well as AC also. So if I charge this with AC source, voltage source, then say the voltage will be like the current in the circuit will be also oscillating current, right? So how do you get the current here? How do you get the current? How much will be the current in this circuit, external circuit? So displacement current means you know displacement current is the current which is inside, and there actually this is due to the change in the or variation in the electric field in between. Okay, so that is, see, the concept is here is that the current, the conventional current or conduction current which is flowing outside the circuit will be exactly equal to the displacement current in between. Okay, in between this will be displacement current. Okay, in between the plates, right? So this is what we have seen in case of amperes. Like, so ampere has given that particular concept here. I'm sorry, Maxwell has given this correction, okay, to the ampere circuital law, right? Ampere circuital law. B dot dl is equal to mu 0 I. So this I is not only the conduction current, it is both displacement current plus conduction current. Okay, the sum of them would be the total current. Okay, so that is what is the correction given by Maxwell. So from here we can say the conduction current is equal to displacement current. So if I can find out the current which is flowing in the circuit, that will give you the answer. Okay, that itself will give you the answer. So how do you find out the current? If you know the voltage here, so if you know the voltage given here is, say, the magnitude of the voltage is given, right, 20. So I know this is 20 volt. Then how do you get the magnitude of the current or amplitude of the current? I have to say this is V0, say. So amplitude of the current will be I0 is equal to V0 by Z. Okay, V0 by Z. So what is Z here? Anyway, there is no L, no R. So Z will be XC itself. Z will be XC itself. Okay. Here the resistance in the circuit will be XC itself. Okay, XC. So we have to find out what is XC. XC means 1 over omega C. Omega is the frequency of the voltage and C is the capacitance of the parallel plate capacitor. See, I know parallel plate capacitor. The capacitance of the parallel plate capacitor can be found out by this. C is equal to, see, this is air capacitance since there is no mention of dielectric material inside the plates. Okay, so epsilon 0 A by D. This will be giving you C. Okay, so what is this epsilon naught? Epsilon naught has got a value. If you want to write down the individual value, that is fine. Otherwise, what you can do, just to avoid remembering this value, let us multiply 4 pi denominator and numerator both places. Okay, then I get a by d. So you have 1 over 4 pi epsilon 0. See, I know this k. So this is 1 over k, 4 pi k, then 1 over 4 pi k, right? And then a by d. What is a? A is 1 meter square given, and d is 2 millimeter. That means 10 to the power minus 3. Okay. So let me just write down these values. Value of the k. The value of the k is 9 into 10 to the power 9, right? So value of k I'll write here 9 into 10 to the power 9. Okay. Then look what we get. So this is 1 meter square. So we have then here 10 to the power plus 6. So which I can write here 10 to the power minus 6 divided by. So this is here 2. Okay, this is 2. This is 8. So sorry, 2, and this is 9. So it will be actually 72 pi into this. Okay, this is actually in terms of farad. Let me find out what is, I'm sorry, let me just remove this portion so that I can do the calculation here. See, I have got C, then I have to find out XC. XC is 1 over omega C. So what is omega? 50 hertz. It is frequency, right? Then you have to multiply 2 pi. 2 pi, excuse me, 50 and C. Excuse me. C, we have got 10 to the power minus 6 divided by 72 pi. So this pi goes up. This will give you 36. Further, this is 18 divided by 25. Now look, this is 10 to the power 6 in the numerator. If I take 100 out of this, then let me write what I can write from here. Say 100, 18 into 100 into 10 to the power 4 divided by 25. So this 25 into 4 will give you 100. So ultimately what we get is 18 into 10 to the power 4. Okay, 18 into 10 to the power 4. Right. So let us see what is the current. So current will be ID is equal to V0, that means 20 divided by 18 into 10 to the power 4, right? So it will be 2 into 10 to the power minus 3 divided by 18. This is 9. So 1 over 9, 1 over 9, I can write this as I don't know whether we have done some mistake. Excuse me. First of all, let me get some space. Okay, with a new slide. Let me get some space. Okay, so we have already got what? See, we have got here 10 to the power 6 by 75, that is my x. Okay, so yeah, almost we are there. Let me then do this thing. Here what we have, 10 to the power 4, 10 to the power minus 4. Okay, 10 to the power minus 4, 10 to the power minus 4 or minus 3. We have got 10 to the power minus 3. Okay, let me do the calculation here after C. Okay, so look what we get. So the current will be ID is equal to V0 by XC. So V0 is 20. What is XC? Omega into C. Okay, what is omega? Omega is 2 pi 50, and C I had got how much? I had got 10 to the power minus 6 here. Okay, 10 to the power minus 6, and here it will be 72 pi. So this pi I strike out. This is 18 then, and this will make this. So what we get is 36 by 5. This is also not that correct. Okay, let me go ahead. What we are getting. Somehow I'm getting the order different. Okay, let me just do this once again. Let us do this once again. See, let us find out what is C. C is epsilon naught A by D. I'll multiply 4 pi. Okay, this is A by D. Fine. So look, this will give you 4 pi here, 9 into 10 to the power 9 here. Okay, then this is 1 meter square divided by 2 into 10 to the power minus 3. Okay, so far no issues. Okay, so what I get, see, 9 into this, I get 1 by 4 pi into this 1 over 18 into 10 to the power minus 6. Okay, I get this. All right, so what I'm getting, minus 10 to the power minus 6 divided by 72 pi. Okay, no issues up to here. What is omega c? Omega c is equal to, okay, 1 over omega c is xc. So let me find out what is omega c. So 2 pi into 50 into c is 10 to the power minus 6 divided by 72 pi. Okay, so this will give you this. Okay, somehow, yeah. So these are fine. This is 36. Okay, so I get 5 by 36 into 10 to the power minus 6. Now let us go to 1 over. So xc is 1 over omega c. That means 1 over omega c. So this is in the numerator. So you will get 36 divided by 5 into 10 to the power minus 6. Okay, I got the point where I was doing the mistake. So let us see. ID will be V0 by XC. So V0 is 20. We'll write directly 20. What is this? That is 36 by 5 into this. Okay, so 36 in the denominator. Numerator it will be 5 into 10 to the power minus 6. Okay, now I hope it will be all right. So this is 10, this is 18, further it will go 5, this will be 9. So what we are getting, 25 by 9 into 10 to the power minus 6. This is the, so this is microampere. Let me get this. So this will be 77 like this. So 2.77 kind of that it will come. I think there is some mistake in the order again. This much is bold, okay, fine. This millimeter, that is also fine. Everything is fine. Okay, I'll just take this up later again. I don't want to further waste my time. So I'm getting something like this, 2.7, something like this I'm getting, but it should be ideally 27.8 or something. Okay, so I'm getting actually 2.78 I'm getting. Okay, so there is some order mistake. Okay, mistake in the order. So just the point of calculation, nothing extra. Only concept was here is that the current through the capacitor is actually the displacement current, and that is exactly equal to the conduction current outside the circuit. That is what was the concept. Okay, so for that we had to find out what is the current outside. Okay, so you have to find out the current, amplitude of the current. Okay, so that's it. Okay, all right, so I think we'll just move on to a quick next problem, and then we'll conclude the session. One more problem we'll go for. Let us solve another problem. So that problem also I'll write it here. The problem says it is actually of general diode. See the problem. This problem is from general diode. Let me first draw the circuit diagram. So this is the Zener diode. As you see, this part will be kind of Z shape, and you have been given a resistance in series. So this is the connection. Let me okay, and there is another resistor, load resistor, it is said. Okay, so this is RS, which is given as 1000 ohm, 1 kilo ohm actually, 1000 ohm. Current through this is IZ say, and this is 100 volt here, 100 volt. Okay, and VZ, that is the voltage drop, or the general voltage is 50 volt, and this is R, which is given as 2000 ohm. Okay, so the question is, for the circuit shown below, for the circuit shown below, calculate the value of Z. Calculate the value of IZ. So this is the question. Okay, you have to find out the current through the Zener diode. That is what is the question. So this is very standard question. You know, for solving this problem, what you have to do, you have to first find out what is the total current this battery 100 volt can send through the circuit. Okay, up at least through RS. So what is the current through RS? So that is IS, let us say. So IS is actually, see the voltage, some voltage is dropped across this, right? If I just consider this much, okay, so some voltage is dropped across this, and same voltage will be dropped across this R, because these are parallel. Okay, these are parallel, right? These are parallel. So if I just consider this way, suppose up this part, if I consider, so IS will be actually 100 minus VZ divided by RS. Okay, this will be the total current, which is up to here, up to here. Then it will be divided into two parts. One is suppose IS, and another one is IR. Okay, so I have to find out IS and IR to get IZ. Okay, so IS is the total current which is sent by the battery, which will be actually divided into two parts. One will go through the Zener diode, that is VZ. Another one will pass through the resistor here, load resistor R. Okay, so what is IR then? IR will be just the voltage drop across the Zener diode, because that is equal to the voltage drop across this 2000. So 50 by 2000. Okay, this will be in ampere, right? So this will give you how much? Let me Okay, so this is actually 25 milliampere. Okay, 25 milliampere. All right. Then here see what is is. Is is 100 minus 50 divided by 1000. So this will give you 50 milliampere. Okay. Now what is the Iz? See, Iz will be Is minus Ir. This will be Iz. So Is is 50 milliampere and Ir is 25 milliampere. So what will be the current Iz? That will be 25. Rest of the current. Okay. So the total current is Is 50 milliampere. This is 25 milliampere. Then rest will be through the channel diode. And say I'll just tell you about the options here. The options are option A 0.15 ampere, option B 0.1 ampere, option C 25 milliampere, and option D is 0.05 ampere. So option C would be the correct answer for this question. So with this, I'll stop it here for today. In the next session, we'll take up some more problems from this particular paper, shift to 1. Okay, so and we'll try to finish as many as possible in the next session. Okay, so thank you for your patience. Bye for today.
This conference will now be recorded.